Okay, so this is supposed to be a follow-on to our beginning of the semester webinar that we had for PICUP that was designed to sort of introduce you to a lot of different sort of, we call it tools of the trade, right? So things that you could use, tools for teaching computational physics or integrating computation further into your physics classes. And presumably you're all here because you have poked around at Jupyter Notebooks a little bit and thought they were useful or interesting, and so you would like to learn more about them. So the goal for the workshop today is to essentially allow you to play around with some of these tools, and so I think what we're going to do, so I'm going to do just a really quick introduction to Jupyter Notebooks and talk about different ways that you can run them, specifically running them locally on, the student's computer, or running them in the cloud using the tool I'm going to use is Google Colab, but there are a number of services that you can do with that. And then most of the time today is actually going to be sort of small groups and people who can work on things. I've got an exercise set from, it's one of my own exercise sets actually, but it's one that's under review for getting included in the PICUP collection. And it'll be a chance for people to just sort of go through and play with it and get a feel for some of the things that you can do. So with that, I think I'll probably go ahead and just give you my quick spiel. So just to get a little bit of a feel for it, how many of you have used Jupyter Notebooks in a classroom type setting in the past? Okay, so most. Jupyter Notebooks are really designed to allow you to integrate computation with sort of the creation of a document. So they're almost like a computational worksheet where you can intersperse code and text and images in some kind of logical way that allows you to work through things. As opposed to a lot of other ways that people use Python, which is more like a traditional programming language, where you have a text file that has the code, and then you run the file, right? So you execute all the code at once, or you execute, you type in a line of code and hit enter and run that, and then you type in a line of code and hit enter and you run that. Jupyter is sort of a halfway point between those two. So it can be used in a number of different ways, but let me show you an example that I actually used today in one of my classes. I gotta share my screen. Okay, so hopefully you can all see that. This is running in Google Colab, which is one of the two options that I'm going to show you here. So Google Colab is running in the cloud, which just simply means it's running on somebody else's computer. This is really convenient at Chico State because we are we're actually both a Microsoft and a Google campus, because apparently we like giving large tech companies lots of money. But all of the students have Google accounts as part of their university account. So they all have automatically Google Colab accounts available to them. And so this particular notebook I put together this is actually for my junior level mechanics class, and we're doing a project where we're talking about linear and quadratic drag on projectiles. And so as you'll notice, this is it looks like a document, right? It has, you know, text, and then it has some code they can run where they do all their importing. And if you'll notice up here, it talks about, there's this check mark, and you can see that it's connected through a web browser interface to a server somewhere in the world that's running my my Python kernel. And so, and you can see it has these little bars that tell you about how much RAM you're using currently and how much disk space you're using out of the amount that it allows you to have in the free version of this code or of this product. There is a paid version of Google Colab as well. I've never used it. And then it has some text. So it tells them, for example, in this case, there's some data involved. They're going to take some data and then fit a model to their data. And so they have to bring in some data, and we can do that. And then it tells them, okay, we need to define a couple of functions. And then I have some notes about things that that they're going to have to do. And then and if we run those, it'll actually run the best fit model, which spit out a quadratic drag coefficient here and a value for the acceleration due to gravity, which you'll notice is less than 9.8, but that's fine because it's a wiffle ball. And so there's actually a significant amount of buoyancy force on the wiffle ball because the plastic is not very dense. And then finally, it'll actually make a plot, and it'll say, okay, there's our data in the red stars. There's our model in the blue line. So the basic idea here is that I can give this to my students, even though these students haven't necessarily had a computational physics class. And while they might not understand each piece of the code, they can get something like this and hopefully do some kind of minimal modifications to it so it works on their data. Or maybe they can change it so that I have several students who are going to drop things through Honey. And so they could change it because in that case, they're going to need to worry about linear drag as opposed to quadratic drag. And so there are things they could change that would make it so that it considered a linear drag model instead of a quadratic drag model. But all of these are fairly minor modifications, and they don't necessarily have to understand everything the code is doing. They can understand bits and pieces of it, and hopefully there's enough text in here that they can explain it. And then they can take this and modify the notebook in such a way that they explain what they're doing in the code, and they can share it with me, and I can see what they've done, and we can collaborate on it. The other way you can run Jupyter Notebooks is running it through Anaconda. Again, that runs through in the web browser. So in my case, the interface is actually running through Firefox, but it's actually running on my computer. So you'll notice the web address here says localhost, blah, 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 blah. That simply means that while it's running Firefox, Firefox is just accessing something being generated by my computer. And so I've got a notebook up, and once again, you can see that this notebook has some code that can run, and it can do various different things you want it to do. So either one of these works just fine. There are some pluses and minuses to each one. Obviously, running it on your own computer is almost always faster. It also has the advantage that your Python distribution is customizable. So if you want to install something that isn't available easily in Google Colab, you can. But at the same time, you have to install it, or your students have to install it. And as I think we've probably all learned, being tech support for your students is a pain. So I prefer to run it when I'm working with students on Colab. But if you have large data files, you want them to do analysis of a decent sized data set, a lot of times it makes sense to run locally. So for today, you are more than welcome to run however you like. But does everyone have access to a way to run Jupyter Notebooks? Maybe I should phrase that the other way. Does anyone not have access to a way to run Jupyter Notebooks? Wonderful. So that's my quick spiel on ways how we can run things. Questions, comments, concerns? Great. So, so what I'm going to do is I'm going to put in the chat a couple of links. And those are links to, so the first one is so the exercise set that I thought we could play around with for today is available through the PICUP website. However, it's not approved yet. It's still under review. And so you can, I believe, get at it, but you may have to be logged in as a registered user. So if you don't have a PICUP account, the other way you can see it is I've put all of the files on a Google Drive account, or my Google Drive, and so that second link should take you to the Google Drive. You should be able to download whatever you need from there. So let me just give a quick overview of what this exercise set contains, the basic idea behind it, and then I think we'll probably split up into a couple of breakout rooms, and we'll just we'll sort of work through this as this exercise set as an example, and give you an idea of the kinds of things you can do with the Jupyter Notebook. So this exercise set, I call it the not so simple pendulum. It is the last experiment I do in a normal year in my intro calculus-based mechanics class. So these are science and engineering majors. Most of them are science or engineering majors. It's usually about 90% engineers, about 10% physics, chemistry. Occasionally we have a geoscience major in there or a biology major. But generally, generally we're talking a little bit of physics and chemistry, a lot of engineers, and the harmonic oscillator is the last thing we do in that class. So we talk about harmonic oscillators, we talk about the pendulum as an example of a harmonic oscillator, and then I give them this in lab as basically what I do is I give them some equipment and I tell them to prove that a pendulum is not a simple harmonic oscillator. And then I sort of turn them loose. And so they have to go through and find a way to come up to design an experiment and collect some data that fits a model of a harmonic oscillator or a pendulum, but does not fit a model of a harmonic oscillator. And it's kind of fun because they get creative on the experimental side. The way that most of them succeed in doing this is by essentially getting to a point where they can, in sort of like a 3 sigma difference, separate the length of the pendulum for the best fit to the length of the harmonic oscillator for the best fit. And I'll show you what that means here in a minute. But that's the general idea behind this exercise set. So can everybody see the exercise set? Great. So I think what I'll do, is I'll split us up into 2 breakout rooms. Well, let's see. 7 of us, and Matteo and Michelle I recruited to help out because I was worried we'd have 15 people, and trying to do a discussion with 15 people is hard. So, well, I'll open up to you guys. Would you like to do this all as a group? Do you want to work? Would it be helpful to maybe split into a pair of breakout rooms? Mark said he needs to leave early.
I'm afraid I have to leave early too, but maybe our group is small enough to be manageable.
So maybe we'll just do one group, and we can just sort of.
I think that's good.
We can just sort of let people work. All right. Well, let's do that then. So, the first thing that I do in this exercise set, and obviously we're not going to do the experiment part, but the first thing that I do is I have them play with the Python code that's pendulum_models, and what it does, if you open that one up, and here I can share that. It actually might be called NSSP_models in your in your file, which I probably should fix. All right, let me share. Okay, so what this thing does is it's basically organized so that they have a whole bunch of parameters, right? So they can give it an initial angle, they can give it a initial velocity, they can give it a damping coefficient, they can give it a length for the pendulum and for the simple harmonic oscillator. And what they've learned, because we've already talked about we've talked about the pendulum, right? Is that the pendulum uses a small angle approximation. So the first thing everybody does, well, if we just run the actual thing, right, with the parameters that are already baked in, we get these two plots down here at the bottom, right, that show a very good agreement if you only pull this thing back 0.2 radians, right? You get very good agreement between the two models. Not perfect, but very good. And so the first thing everybody does is they come up here and they say, okay, I need to get them to disagree. So how do we get them to disagree? Well, of course, we make the angle bigger. So I don't know. Let's go to a really big angle. Right? And then I rerun everything. And we see, aha, they disagree. Right? So that makes everybody feel happy. However, and I have them then say, okay, can we make them agree again if we mess with the lengths? So one of the things that that turns out to be a fun feature that nobody generally tells you is that you can make the pendulum and the simple harmonic oscillator look very similar if you change the length of the pendulum. So if you go down here and you look at the plots, right? So here's our angle plot. The pendulum just looks like it has a slightly longer period than the harmonic oscillator. So, being as we're smart physicists, we know that if you just make the length a little bit longer for the pendulum, you can make the thing look longer. And by the way, I'm going to stop running the middle one because I actually don't need to redefine the functions every time. And when this thing runs, okay, I need to stretch it a little bit further. Come on, thing. Let me scroll. There we go. So still my pendulum needs, or my pendulum has too long of a period, right? So you can play around with that. So play around with it a little bit, see if you can get everything to run, and see if you can make the two match. And once somebody's got a good match just by changing the length, let me know.
Looks like I can only get a good match for the first few cycles.
Yeah, and so you can get the period to match pretty accurately, right? But the point I'm actually trying to teach the students here is that in a pendulum, the period is actually dependent on the amplitude, right? Whereas a simple harmonic oscillator, it's not. So the trick here, what they need to be able to do to make these two, to make a situation where you can't get them to match, is they need to have something that changes amplitude, right? They need damping. So they need a few things. They need a fairly big amplitude. They need damping. And they need enough damping that it can drop over time, right? That they can get enough cycles without their data, right? So for example, they need to be able to collect maybe 20 seconds of data. So they can play around with these things. So the next piece, right, is then they actually go and they have to run the experiment. They have to try to actually make a physical thing that kind of looks like this, right? And once they've done that, then they can come back and they can run the other part of this, which is the NSSP_model and data notebook. So what that one actually does, let me share my screen again. Is again, they have to give some guesses, right? And I tell them, just give me some guesses, right? It's not really, these are the initial guesses for a fitting procedure. So it's actually not that important what the values of these guesses are. However, as anybody who's ever done fitting knows, if you give it bad guesses, sometimes it fails, right? And that's actually one of the things that students dislike, is when it fails to fit. But then so then this is actually a piece that I think is worth spending a little bit of time on. So I mentioned this earlier, but this is one of the things that is nice about using Google Colab. Well, okay, it's actually a downside, but it's a nice workaround for the downside. If you're running Jupyter locally, you have access to all your files, right? You can read in files very easily. If you want to run it in the cloud, those files have to be made accessible. And you can do that in Google Colab with this gdown command, which is essentially a Google download. So you give it a web address using this file ID, right? And then it will actually go out and it will download that file. And then that file will be in the working directory of this notebook on whatever server it's running on off in La La Land. And you can actually access the data from there. So, so if I go ahead and run this thing, I actually probably should run that too. It's gonna have to think for a second. If it's a big file, it will take a little bit, but it's pretty fast because it's Google downloading from Google. So it should be decently fast. And then we go through and we import libraries, we define things. And then we actually run the thing. Right? And this one actually takes a minute. You'll notice that it's a noticeable amount of time from when you click the play button to when it actually gets done. And what it's done is it's fit a harmonic oscillator model to your data and a pendulum model. The harmonic oscillator is actually solved using the same differential equation solver numerically. It doesn't have to be. Obviously, you could give it analytically, but I think it's kind of nice just to get them used to the idea. And then it says, okay, here's your best fit. There's your two lengths, right? And you could actually plot your data. And, you know, in this case, they're almost identical, right? Now, they're not quite identical. You'll notice that the lengths were different, but the lengths were only different by 5 centimeters, right? So I tell the students, are you really confident that you've measured to the center of mass of your pendulum to plus or minus 5 centimeters or 2.5 centimeters to either side? And, you know, they're not. Sometimes they are, but maybe they shouldn't be. But the nice thing about this is that then they can go back and they can play with it, right? And you can actually, so let's say you give them a bad initial length guess, right? Instead of 1 meter, you give them 10, you say my initial length guess is 10 centimeters. You don't have to re-download the file. It's still available, so you don't have to rerun that particular piece. But we do have to rerun the actual fitting procedure. We do rerun this thing, and you'll notice that it's going to have a rough time. Because for some reason, the pendulum fit was just fine, but the harmonic oscillator fit was terrible, right? And so they have to play around with that a little bit, right? They have to fiddle with that. And you'll notice that the harmonic oscillator fit, right? It just, for some reason, the pendulum was okay, but the harmonic oscillator wasn't. And why? And I don't know, because it was a bad guess, right? And if you want to teach them computational physics, you could go into all that. So anyway, you'll notice in that file, right, there was another data file. So let's see, let me get the name right. The other data file was called small angle. Oh, I'm sorry. There was one called large angle and one called small angle. So why don't you play around with it and see if you can get it to work for one of those two data files. So you'll have to, if you're running this on Google, you'll have to upload the file to somewhere you can access it. So Google Drive, for example. And then you'll have to modify the code and get it to download. So I'll stop talking for a little while and let people work. And if you have questions, please let us know and we can help.
So I have a question, Nicholas.
Yeah.
Before I kind of have to bug out, but so some of these, I'm looking at the NSSP model and data, and this is mostly blocks of code. There's a little bit of reminder up top about remember how to download a file. So in this, for this kind of thing, that's mostly chunks of code. Can you talk a little bit about the benefit or the, using Jupyter as opposed to using Spider, just an editor?
Yeah. So I actually, this particular code originated as using Spider. I moved it over 2 semesters ago and had the students use Jupyter instead. And I had them actually insert explanations as they went through. So they had to explain to me, and particularly I'm looking at like the blocks where it actually runs the fitting procedure and where it prints things, right? I want them to basically insert some text there. And actually, I should probably let you guys see what I'm doing.
Okay, so that makes sense. So they're inserting
so they're inserting some comments,
yeah.
right? And this case is sort of, I mean, this may not be the best example simply because I'm using, this is one where they've already seen bits and pieces of code over the course of the semester. And this is sort of the end. So I want them to explain to me what the results are and why. So for example, I tell them, I want them to basically keep a running list of their guesses and the oscillator lengths. They're the length of the pendulum and the length of the harmonic oscillator that come out with those choices, right? So for example, they could say, I tried it with an amplitude of this and, I got these values and, they're not far enough apart. And then they would say, okay, so then I ran it again with this, this other amplitude, or I strapped a piece of paper on the front of my pendulum to give it more damping, and I got this. But there's some idea that they're kind of keeping a record in the notebook.
Okay, thank you.
I will say that that for me, it's been sort of a slow process. Last semester was the first time I just had them turn in the Jupyter Notebook. Previous to that, I would have them copy things over into a Google Doc. But the nice thing about going to Colab is that they can share the document with each other. And it's not quite as slick as Google Docs, where you can actually live edit the same document with multiple people all at the same time, but it's pretty close. So if I make changes, you can see them, and you're sitting there with the thing, you can see them, but it's not quite live. Sometimes you have to reload things. Sometimes you can't tell where somebody else is working. Changes will just sort of show up midway through. Other questions? Oh, no problem. So maybe just more generally, we've got a few minutes left. We can just sort of open it up to questions. So maybe Floyd and Stan, if you guys have questions or want to talk about ways you're thinking about using something like this in your classes.
You hear me, Nicholas? I'm
Yep.
trying to. One of the things that I just started reading about this stuff just about 9 months ago, and kind of enthralled not only by computational physics, but computational thinking as in a whole bunch of different environments. And one of the things I've noticed is there appears to be kind of two different schools of thought in this. One is computational physics or computational thinking is integrating this like you just showed. The other, though, is when my students, I tell you, they have a hard time figuring out how to think in the abstract. They have a hard time thinking about just how to solve problems. And the nice thing about programming is you have to gather all your data before you can write a program. Many times when my students are trying to work a problem, they don't, they will find every equation they can find and every piece of data they can find and just kind of throw them in a mixmaster and hope that something happens. It strikes me that computational thinking and computational physics is it's a new way of thinking about problem solving. It's not just integrating computer programming with physics, which is good by itself, don't get me wrong, but there's another part of this process which is even more valuable, and that is taking the thought process that you use in programming and using that as a way of structuring your problem solving. Is that something you guys have ran across? Because I run into these two. Whenever I have this discussion, it seems like most people gravitate towards, oh, you're going to write programs to solve problems. Well, yeah, but I'm going to use that thought process that I used in programming. By the way, I've been programming since 1965. That's when I learned how to program. So you know what my main language is? Fortran, of course. So anyhow, what's your thoughts on that?
I don't know, Michelle, do you want to give thoughts on that?
So, I mean, can you more like was there a question in that, or like, because you're asking about computational thinking and the process, right? Or the reason that we're integrating computation?
The question, Michelle, is this. Often there appears to be two schools of thought with regard to computational thinking. Mm-hmm. When what's her name, Deborah Wing or whatever, Wing, the lady that had the paper back in the early 2000s, a lot of that seemed to go towards what we're doing here. Integrating this stuff, but I got a hint of the other part of this process, which is more what I'm seeing along the lines of what, who am I thinking of? Wolfram. When Conrad Wolfram, not Stephen Wolfram, Conrad Wolfram wrote the paper on the new maths, where it's a thought process. It's not just a mashup of physics and computers. It's a completely new way of thinking. And what I'm hearing more often than not is this mashup, rather than a completely, using the thought process you use when you do develop a program, using that thought process in the way you structure problem solving in general. And the question really is that, do you see that dichotomy? Do you see us doing that? You're nodding your head, so I'm going to shut up and let you talk.
Yeah, so I think that that the people behind and the people that use the Matter and Interactions book, I think that they were kind of having this, you're thinking about solving a problem from the get-go of learning physics in this different way. I think so yeah, I see it. I see people taking that approach. I think me personally, to me, computation is as much of the process of doing physics as mathematics today. So to me, it's just one of the languages of doing physics. And so I don't think of it as a mashup, but just as a part of even doing physics, which isn't as much a focus on the thought process, although that's something, I guess that's an outcome that I hope happens, but I personally don't target it in the way that I think some people intentionally do, which is obviously like a great way to go about it. I don't know, Nicholas.
Yeah, I'll agree with that. I generally, at the intro level, I tend to introduce computation as a tool, right? I mean, it's primarily a tool for, I tell them, you know, you're done with hand-drawn plots, right? Don't draw plots anymore. Computers can make plots. You should learn how to make a computer draw it for you, because it will be better and it will look nicer. And someday your boss will think it looks much better than when you tried to sketch it by hand, right? And so I present it to them as a tool that will make their life easier. And then, so like, for example, in my intro class, their first exposure is just plotting, right? That's all we do. And then I introduce them to curve fitting. And again, it's a very black box sort of approach. It's just, here's a tool that if you define a function, it will figure out the best values of these parameters to make your function look like that data you have. And then the next piece I bring in is and again, in a very black box sort of way, but I bring in linear systems, right? So when we do statics, I show them you can build a trestle that very easily becomes like an 8x8 system. And I demonstrate to them that solving a 3x3 is a nightmare. But hey, look, computers are good at this. And so I teach them, okay, here's again, in a very black box sort of way. And my goal primarily at the intro level is not to teach them to program. My goal is to teach them to do physics. And as Michelle said, to see the computing and analogous to the math, right? That it's just doing math in order to solve physics problems. It's just letting the computer do the math. So you have to teach the computer to do the math. When I get to the upper division level, that's when I want to actually teach them to program. So that's when I introduce things like generating code from scratch, or giving them a very bare bones example and saying, I want you to plot things now. I want you to, I want you to do add a differential equation solver or whatever the thing is. So for me, it depends a lot on where I'm teaching it, but I will say on this sort of algorithmic thinking note, I think you can't help but get some of that into your process when you start adding in computational tools, because you can't program without it. At least not in any sort of, well,
I have seen over my years people who manage to program without thinking.
Okay, well, that's probably true. You can't.
Oh, I see that a lot, actually.
But in order to program effectively, maybe is what I'll say, you almost are forced into thinking about things in a different way. And so, so I don't know, I feel like it helps, but again, that's not my primary purpose when I'm doing.
Yeah, I agree about 3/4 with you in that this is a tool just like math's a tool. Math, I can't think about the pendulum problem unless I have an understanding of math at a level beyond A plus B equals C. Now, the problem that I run into is my students, getting them to think in the abstract is very difficult. In fact, I was shocked. I started teaching when I was 70, okay? So I'm an old guy new to a profession. And my second semester, when they decided that I could probably teach some engineering courses, I taught dynamics. And what I was appalled at is these students didn't seem to understand anything except, give me some numbers so I can plug it in so I can get an answer. And I said, I've got a thing here in my hand. I can use Wolfram Alpha, and I can do that with this. Nobody's going to pay you to plug in numbers. You need to understand how to do it. So that was my first introduction to people who really couldn't work their way through solving a problem. They could only work problems. And so what I've been struggling with is how to get these students to think about problem solving instead of just some problem working. And so I will give them a structure, define the problem. What do you know? What don't you know? What's the, what are the equations you're going to use? And it is difficult, even if I give them that outline, to keep them inside the lines filling those things in. They will again go back out, and if I gave them 10 equations, 3 of which were of value, they would figure out some way to use all 10 equations with any numbers they could find to get answers. And so the structure that I'm talking about, the programming brings to this is, unless you work for Microsoft and you put things back in, put Easter eggs in there, the stuff you put in a program is stuff that's required in order to make the program work, period. If it's obvious when you're writing a program, if I have 15 variables up there that I don't use, then they're not a part of the problem. And the algorithm uses those. And so the structured thinking that is computer, who is it? One of the guys, think like a computer scientist. Well, when I first saw that, I said, oh yeah, right, another buzzword. But I think he's absolutely spot on now. And that is, I've got to think about how I structure my knowns, my algorithms, and my output. And so anyhow, that's what I'm looking for, and trying to get, using Jupyter, trying to get that structure of thought process as well as code integrated, which is what you've shown in these things. By the way, I like those things. I will try and use those. I would love to see a textbook that's written this way, because I think I could get my students at least to start thinking about how they solve problems. They could see that connection, the ability to use LaTeX and write the equations in my text and then go down below that and execute it. I think it's a powerful, powerful tool. And so like I say, I agree with about 75 or 80% of what you and Michelle said. But the part that I think is equally important is this part on top, where they think like a computer scientist when they're actually setting up the problem. I think that'll be of value. So anyhow, my daughter tells me I preach too much, so I'll be quiet. But I appreciate this community that I've now become a part of. This is great.
Yeah, I agree with you totally. And definitely have a look at the Matter Interactions textbook if you haven't seen that. I actually don't use it. I'm offering up advice that I don't take, but it is a textbook where computation is embedded into the material from the beginning, and it follows the ethos of what I believe in, even though I don't use the textbook. So definitely take a look at that.
Okay, thanks.
I'll also add that one of the things that I didn't mention, and Stan actually brought it up, which I should have, is that because these notebooks have, it's Markdown is the text language, which, by the way, in the Google Colab environment, it actually structures the text with all the tags built in, or almost all the tags built in as little buttons up at the top. So it looks like kind of like a rich text editor, but it's actually just doing Markdown, which Markdown can do not all LaTeX, but it can do quite a bit of LaTeX, and particularly the stuff for formatting equations, which is really nice. For some of my upper division students, I make them take advantage of that. I make them write out their equations at the top of their notebook, because one of the things that I find is hard even for junior and senior level students is to take an equation and actually just like make the computer plot that thing, right? And so translating it from math, which is a format they're used to code, which is a format they're generally not used to, is a little bit of a trick. And so it's my workaround for the problem of I get homework assignments where they've done everything right, but the equations they're solving are wrong. This sort of is a help there. I will say though too, it depends a little bit of which class you're teaching, because Stan, like you're talking with dynamics, you know, those are students that have already had presumably several semesters to sort of get thinking about things, right? If I could get my intro physics students to think algorithmically, I would be thrilled.
Yeah.
My intro physics students, I'm usually just happy if, you know, they don't throw up their hands and run away when they see algebra. Because, you know, they've had calculus, but somehow they're still terrified of you know, an algebraic equation.
Yeah, you can pass calculus without doing algebra.
Yep, and somehow they all managed to do it. And well, not all. I'm being mean. Yeah. But I will also say that that one of the benefits of the format, because I tell my students all the time, look, I'm pretty confident that if I just give you a math equation, you'll figure out how to solve it, right? I mean, you've all passed math classes. You'll figure out how to solve it. You'll put in numbers. You'll do something, you know. And so what I'm more interested in is, can you explain to me why you picked that equation? Yeah. And so the ability to make them comment, essentially, to have these blocks of text where they have to come in and say, okay, you know, I think that I should do, you know, -1/2 g times squared here because we're in free fall and I'm trying to calculate position, is almost as valuable as actually getting the answer out at the end. Maybe more valuable.
Yeah, you know, it's interesting. My students are so, well, they're pretty siloed in their thinking. You know, I passed calculus, so I don't have to worry about that anymore. I can come over. Then when I get them in a physics class, I have to teach them calculus kind of over again. And I have both the college physics, which is physics without calculus, which to me is, I don't understand it, but I teach it. And then I have the university physics. And then we're a small college. We just are starting with our engineering. But, you know, you say that they, where was that going? That the ability to think abstractly, in other words, the ability to draw on that math, because I will do kind of like what's on your board behind you. I'll work through the things and I say, well, okay, now you know how to get from here to the answer. So let's go on to something else. That drives them nuts.
Oh, yeah.
Because they will, I say, you know, they'll tell me you've only done half the problem. I say, no, I've done the whole problem. My computer can do the rest of that stuff. That's just arithmetic. And oh my gosh, so I think this computational, this part is the 80% you guys are talking about. I think this part can give me some hope in that regard. If I can teach them how to, you know, okay, here we go to this, then you can just plug this into even Excel, by the way, folks. Excel is a pretty powerful tool that they can visualize more stuff with Excel. So yeah, that abstract thinking is kind of hard. You were going to say something, Floyd. I could hear the wheels turning.
I was just listening to your comments because, yeah, it is true that the math skills are weak. If you're doing problems on the board, you know, the physics problem, there's like 3 lines of physics. Then there's a bunch of math. And then there's an answer at the end, which is the physics again. So I'll do the 3 lines of physics. I'll go to the bottom, do all the steps in between. Oh, they just go crazy.
Yeah, but don't you think that this things like this Jupyter Notebook can give them that in-between stuff in a way that helps them see that top and bottom stuff?
Well, my question is, can computation help us solve problems without them knowing the math, which they don't know?
Oh, yeah, that's a good question. I think that, what do you guys think? I think that's crucial. Michelle, what do you think? You're nodding your head like you have big opinions.
Well, you know, I like one thing I've been really thinking about in recent years is whether or not we focus too much on analytical math in the physics curriculum. Like I teach modern physics. This also happens in second semester calc-based intro, where the math required to solve the physics problems just gets unwieldy. Like you get to the hydrogen atom and then boom, your semester's ahead of where they've taken math, and you're in 3D vector calculus once you get to certain geometries in in second semester intro. The physics they're capable of, but we spend so much time on the analytical mathematics that I sometimes wonder, like are we achieving our learning goals by spending so much time on the mathematics? It's just something that you know, Floyd said that resonated with me, because I think about it.
See, I know how to multiply numbers by doing logarithms, but you all don't do that anymore because you use calculators. So why should you do integrals and derivatives when the computer can do them also?
Yeah. And I mean, I think though it's really important to note. So like what I do is in my intro classes, I introduce computation as like, I don't even tell them they're programming in Python, but they are. And I'm like, this is a cute way to help you like do your work. It's faster. And then they have to take computational physics in their sophomore year. And it's like, well, actually like we're programming. And then we start getting into things like, okay, yeah, it's like magically give you an answer for the integral, but let's talk about what's doing behind the scenes. And then you have like numerical issues and things that you still have to know that an integral is the area under the curve, and how you calculate that area, you should be aware of, because you can get issues, right? Incorrect answers. So there's still discussions that need to be had about mathematics, but it's just what is the way to do that, I guess.
Yeah, I'll chime in on this. So I actually, if you notice in that, the thing we looked at, right, it's having them solve differential equations, but they don't know how to solve differential equations. In fact, most of these students don't know what a differential equation is. And what I like to point it out to them just to kind of get them, after they've done this, I point out like, okay, this is an equation where the answer is not a number, the answer is a function. Right? Which they don't even know, like they can't even really wrap their brains around that. But the fun thing is they don't actually need to know how to solve differential equations. They can just say, okay, here's, you know, what we need is we write the equations as a system of first order equations. We need the right-hand sides of those. You put them in here and you're off. And then they can solve any differential equation, right? Nonlinear differential equations, fine, right? Solve whatever. And of course, they don't know what it's doing, right? But to me, that's less important. That's something that I'm going to teach them if they come take my computational physics class. What I want them to know is that there's physics here, so they have to figure out how to set up the problem, which is the 3 lines of physics at the top, and they have to get the plot or the answer at the bottom, and the computer handles a lot of the math in between. So, you know, I think you can go too far that way, because I think maybe we overemphasize analytical math, but I don't think you can do physics without analytical math. But maybe maybe we don't need to spend as much time as we do on it. I'll give you another example, and that is the quadratic equation. Like getting students, when I say quadratic equation, like my students all have flashbacks to like 10th grade, because they solved it, but they didn't know why or what. They know the little jingle that they can sing that tells them the quadratic formula, but they don't understand it. And I point out, it's fine. Just, you know, plot the thing and, you know, zoom in on the plot and, you know, see where it crosses 0. Problem solved, right? And they don't, some of them don't like that because they feel like it's cheating somehow. But I point out, no, it's just, if you need it more exactly, just, you know, add some more points, zoom in on that spot, you know, you're fine. And you can get the answer more precisely than you will ever need in your engineering life. So So, I mean, there's some advantages there. I think it's a little bit of a balance.
Well, thanks
I
for
have
the
to
work.
run, but it was really great seeing and meeting you guys. Floyd, if you ever need like a seminar speaker from in-state, let me know.
We do. Send me an email.
Too far.
Okay.
Okay.
Nice
Well,
to meet
thank
you
you.
all.
All right.
Now,
Thank you, Nicholas.
Well, thank you. I appreciate you guys coming and bringing your questions.
Yeah. Good to meet you, Floyd.